Hello and welcome to the next segment of the degree theory presentation. Let me remind you that we are talking about the local Brouwer degree, and today's topic is the uniqueness and the existence of the degree. Let's start. Uniqueness and existence of the local Brouwer degree. And to start, let me formulate the first lemma. So let's put V is equal to Rn. Suppose omega is an open bounded set. So here we have belongs to, so it's contained in V and B. Okay, maybe let's put and omega, and let omega contained in V be an open bounded set. So consider two admissible pairs and put it like this: F omega and G omega, so two halves, such that let me say it like this, such that F and G both are defined on on V to V are C infinity differentiable and omega admissibly homotopic. Then there exists let me formulate it like that. So delta tilde, maybe write it down like that: 1/2 is larger than delta tilde, larger than 0, such that, and maybe like the there exists properly, there exists delta tilde 1/2 larger than delta tilde larger than 0, and C infinity, so C infinity differentiable omega admissible homotopy, and we can write it down: H tilde defined on 0, 1 times V to V, satisfying the properties So the first property is that, call this one A, that H tilde of T of X is equal F of X for 0 smaller T smaller than D delta tilde and X belonging to omega closure, and B, that H tilde of T of X is equal to G of X for 0 smaller, and that will be 1 minus T also smaller than delta tilde, and X belongs to omega tilde. So basically in this statement we just simply say that any homotopy of two smooth maps F and G can be corrected to a smooth homotopy. Moreover, this smooth homotopy can be done in such a way that for small t, this is a constant homotopy. Sorry, for the t not far from the endpoints 0 and 1, this is a constant homotopy. So it keeps these functions f and g unchanged. So let's do the proof. And let's begin. So suppose we have here a homotopy. So suppose we let H1 from 0, 1 times V to V be the postulated in this, let's say in this lemma, there are F and G, CG, and admissibly homotopy. So this is a homotopy, be an omega admissible homotopy. Omega admissible homotopy between F and G. F and G. So since this is admissible homotopy, so we can choose epsilon and we can put. So that's only continuous. We need to correct it to the smooth homotopy. So put epsilon 1 is equal, and I put here 1/3, and this will be minimum by admissibility. So this is Tx belongs to the 0, 1 times boundary of omega, and I put here H Tx. So that number is definitely positive, and remember this is 1/3. And next, by Weierstrass theorem, every continuous map can be approximated by the smooth map. There exists a C-differentiable epsilon 1 approximation epsilon 1 approximation call it like this, H1, this was H1, so call this one H2, that goes from 0, 1 times V to V of H1, at least on 0, 1 times omega closure. So this is homotopy, require homotopy. So we claim, notice that by this condition, call this condition 1, that by 1, H1 is omega admissible. Indeed, for every x and t belonging to 0, 1, and this is boundary of omega, we have. So what do I have here? I have here H2, this is Tx. So let's rewrite it down. This will be H2 Tx minus H1 Tx plus H2 H1, maybe make sure this is 1 H2 Tx, and now that one is larger equal, I put here H1 Tx minus H2 Tx minus H1 Tx. So what do we get here? So we are getting that that one is larger equal than this minimum, and this is Tx belongs to the 0, 1 times boundary. So that one is H1 Tx, and that one is minus, and we know that's epsilon 1, but epsilon 1 actually is strictly smaller, so we can put it like that. So this one is strictly smaller than, copy it again, minimum Tx here, and that one is 0, 1 times omega. This one is H1 Tx minus 1/3 of minimum, and this will be Tx belongs to the 0, 1 times boundary, and here we have again H1 Tx, which implies that, and call this formula 2, that absolute value of Htx is strictly larger than 2/3 minimum Tx belongs to 0, 1 times boundary, and that one is equal this is 2, Htx, and that one is 1, maybe 1, this is 1. So definitely larger than 0, So we have it. So that means it's admissible. Next thing. Notice that in particular we have the following. So if you take, for example, t is equal 0, so in such a case f of x, and I put here like this, minus h2 t of x, because this is epsilon 1 approximation, so that one will be smaller equals than epsilon 1 for t equals 0. And similarly, for t equals 1, we are getting here that g of x minus h2 t of x, that value must be smaller than epsilon 1. So this is epsilon 1 as well. So these two values are. So now, by the continuity of h2, just by continuity, so we can basically say that there exists by continuity of h2, there exists a mu larger than 0, maybe we should keep it in mind that 1/2 is mu larger than 0, such that, and let's put it, this will be my third formula, such that here we have here, for every x belonging to omega bar, and then for every t such that t is 0 smaller equal than t smaller equal than mu, we have here f of x minus h2 t of x, and now I just take 2 epsilon. 2 epsilon. So that means if it's satisfied, so just by continuity, you can find mu sufficiently small so that this will be satisfied, and 0 smaller equal 1 minus t smaller equal to mu will give me g of x minus h2 of tx smaller equal to 2 epsilon 1 as well. So these two conditions now we will use. So we have here mu, so let me show you what we are actually having, and maybe we need to define an auxiliary function. So let me just simply define this function as follows. So maybe that will be a function defined like that. We defined it like this. So we defined an auxiliary function C infinity function, and call this function phi from R to 0, 1, such that this function is satisfying the properties. So this is phi of, maybe put here S is equal to 0 if t is between 0 smaller than delta tilde, which is strictly smaller than mu over 2, and it will be 1 if t, sorry, I didn't write s, so smaller equal, this is s, and this one is smaller equal than delta tilde, which is assumed to be strictly smaller than mu over 2, so we can always construct such a function. So this will be 1 in the case when s is larger equal than so let's say like this, maybe write it down that way, 1 minus s is larger equal than 0, but smaller equal than delta tilde as well. So let me make a picture, show you the graph of that function. So this function looks like that. So here we have here the interval. This is my interval. This is 0, and that one is mu. Here we have here delta. This is my delta tilde standing here, and this is 1 minus delta tilde standing here. Here we have here, maybe put it here, 1. This one is 0, so this one is a function that looks like that, and it's smooth. So this is my function phi of s. So as s is here, so that's function. We have 0 here, it will be 1. Here it will be 1. So once we have here this function, so we can define. So we defined and we define the required homotopy And this homotopy will be just defined like that. So I put it like this: is Tx is equal, and we have three cases. So here I put here 1 minus phi of t, and here will be f of x, and this will be plus phi of t, and this will be h2 tx, and this will be in the case t is smaller equal than t is smaller equal than than mu. And the second one will be exactly 1 minus phi of t. So in this case I will change it maybe conveniently to 1 minus t, and this will be g of x, and this will be plus phi 1 minus t h2 tx, and this is smaller equal than 1 minus t smaller equal than mu. So that's the second one. And I have a third case, and the third case is just simply equal h2 tx otherwise. Since h2 and phi of t and phi are C infinity functions, the function, the homotopy h tilde is also C infinity. We claim that this homotopy that h tilde is omega admissible homotopy. Notice the other two requirements are satisfied by the definition, because here this requirement will be just guaranteeing. First, look at the definition of the function h tilde. So this will guarantee that for 0 t smaller equal than delta tilde, this will be f of x. And similarly here, if 0 smaller equal 1 minus t, again t tilde, this will be g of x. So this requirement will be satisfied. So we only need to prove that this is an omega admissible homotopy. That's what we are going to do now. So now let me just write it down. So by the definition, so for all, and put it like this, tx belonging to 0, 1, so maybe call it indeed, times boundary of omega, we have. And then we have here, let's put it like this, h tilde tx, which is equal, well, that will be equal h2 tx minus, and this will be phi t, and we have two cases. So maybe let's say this is for the first case, is that this one is smaller than m, t is smaller than mu. So the other case you'll be just doing exactly similarly. So this will be equal to f of x minus h2, and this will be h2 t of x. So now we can rewrite it smaller equal, so this will be h2 t of x, like that. And this one is minus, and I can just drop the guy here, so this will be phi of t smaller than 1, so maybe let's write it down first, that one, and this will be f of x minus h2t of x. So now, let's rewrite it. Again, another inequality. Look that we have here by inequality number 2. By inequality number 2, this is this inequality. We have, and this is the inequality, call this one here star. So that one, inequality star, so maybe like this. So this is by 2 and star. We are getting here that that one is larger, actually strictly larger. So this is strictly larger than 2/3, and this is minimum, and that one is equal t of x belonging to 0, 1 times boundary, and this will be f1 tx original minus, and then you have here that one is 1, so the first one is smaller equal than 1, and that one is actually epsilon 1, so I can put it like this, smaller equal than 1/3 minimum sorry. No. 2/3 by the, let's see again, you see, by that one, because here is this guy. So this is 2, sorry. So this will be 2/3, because here t is more equal than mu. So this will be 2/3, and again, that one is equal. Tx belongs to the 0, 1 times boundary, h1 tx, and everything gives me 0. And since we have here strict inequality, we proved so. Indeed, h tilde is omega admissible homotopy. And that simply is the end. We proved the required lemma 1. And this lemma 1 is needed to prove the actual lemma that we'll be using in the proof of the existence theorem. So let me put it here, lemma number 2. Lemma 2. So suppose, or we let, like it was before, f omega and g omega be two admissible pairs such that, and I put here like this, first condition, 1, f and g have 0, so maybe restricted to omega bar, have 0 as a regular value. So in such a case, we just say that these two, maybe for the future references f and g, we call it r, omega bar regular, or regular in omega bar. So that's how we can call it in the future. So this will be 2 f and g are omega homotopic, maybe like are homotopic, baby, are homotopic, baby, homotopic by an omega admissible homotopy, omega admissible homotopy. Then we have the following. Then there exists delta, which is smaller than 1/2, strictly larger than 0, and a homotopy and a C infinity homotopy, a C infinity differentiable. And this will be H from 0, 1 times V to V, such that first one, A, 0 is a regular value of H, and this is restricted to 0, 1 times omega bar. And B, H of Tx is equal to f of x for 0 smaller than t and smaller or equal than delta. And here we have x in omega bar, and C H of Tx is equal to the g of x for 0 smaller 1 minus t smaller or equal than delta, and again x belongs to omega bar. So that's a ring finite. So that means what we are proving here that any homotopy between f and g can be, in the case f and g are regular, can be replaced by a regular homotopy, also satisfying the condition that is constant near the endpoints of the homotopy. That means near t equals 0 and near t equals 1. Near t equals 1. So this is our lemma. So put it like this: proof, and let's continue. So by lemma number 1, there exists a homotopy, and we have this H tilde 0, 1 times V, and this is 2V, such that, now let me write these conditions such that we have here like this. So first of all, C infinity homotopy such that, so we have here C infinity homotopy H such that, so first of all A, so this H tilde, maybe just call it such that H tilde is omega admissible, and we have here two conditions: H tilde Tx is equal to f of x if 0 smaller t smaller than delta tilde, and B, H tilde of t of x is equal g of x if this is 0 smaller 1 minus t smaller than delta t. So we have it by lemma number 1. So by lemma number 1, and now let me construct, let me correct this homotopy to a homotopy such that this will have a 0 as a regular value. So we are constructing homotopy H that will have a 0 as a regular value. And in order to do it, so first of all, let me construct a smooth function. So let us consider a smooth function means C infinite function, C infinitely differentiable function psi that goes from R to R, and this function will look like that. So let me make a picture now. Now we consider here sorry. And this is my not nice. I try to make it a straight line. And this would be 1, this would be 0, this would be 1 standing here, and now we have here delta tilde here, and here is also 1 minus delta tilde standing here. So now we choose here, let's say like this, delta. So this is my delta, 1/3 of that one, and here will be another one. So this will be delta tilde minus delta. So here we put here 0. So here will be value 0. Similarly, I put here 0. And then starting from here, from the other point, that one, and from that one, the value will be 1. And then I make it nicely smooth. Not nice. This is not nice. Nicely smooth. Such a function. Okay, so that's my function. This is nicely smooth function, so maybe you can write it down. So we have here psi of S is equal to, so we have here delta is smaller than, maybe put it like this, delta is equal delta tilde by 3. So then this will be equal 0 if S is between and delta, or if 1 minus S is between 0 and delta. And it will be 1 if delta tilde, so put it like this, delta tilde minus T, so the minus S is smaller than delta. And similarly, if 1 minus delta tilde minus S, so this is, so where it is, this is here, so that let me, this one is here, so 1 minus tilde plus S is it's like this, or I'll just simply write it down. So 1 minus delta tilde plus S is smaller equal, so this is larger equal than 0, smaller equal than 1. Why not? That's it. So that means no. Minus plus delta tilde plus delta. Okay, something like that. That's exactly how it is. So such a function is, you can easily construct if you don't know. That's a good exercise to construct such a function. And now what we do is the following. So by Sard theorem, the set of all regular values of the h tilde, and this one is 0, 1 times omega r, is open and dense, in V. Therefore, for every epsilon, and we will specify the exact value, the exact requirement on epsilon, so put it this, we will specify the requirements on epsilon later. There exists a regular value and let me write it down, y belonging to a regular value, y belonging to V of h restricted, h tilde restricted to 0, 1 times omega, such that the norm of y is smaller than epsilon, Good. And we define the candidate for our homotopy, so put it like this, h that is written like 0, 1 times V, and this goes again to V, by the formula, so this will be h tx, and now that's the old homotopy, and now we are correcting it. So we are correcting it using the minus psi of ty, minus psi. We are correcting it to the homotopy that has a regular value. 0 as a regular value. So let me formulate the claim. We claim that for a sufficiently small epsilon larger than 0, h restricted to 0, 1 times omega has 0 as a regular value. Of course, we can also choose this epsilon sufficiently small in such a way that h will be also omega admissible. So we will prove it as well. We will prove it as well. 10 and regular value, and h will be omega admissible. Notice that the formula is constructed in such a way that that function is 0 near the end points for t equals 0. Maybe I'll change it to red to write this remark. So for t is equal 0, for t is equal to 1, near this point, this will be exactly h tilde, and 10 means this will be f, and that will be also g. So it will be locally constant near t equals 0 and t equals 1. So that requirement is no problem. That requirement, of course, we also know that by taking epsilon sufficiently small, we can also assume that this will be omega admissible. So now, the only thing we need to show is that this will be regular value. So how to choose, how to find appropriate epsilon? How to find appropriate epsilon? So let's begin. So notice notice the following. So put, and this is going to be k0. By the definition, it will be f minus 1 of 0 intersection omega, and k1 is equal to f minus 1, sorry, not f, g minus 1 of 0 omega. And since we assume that f and g are regular maps, that means 0 is a regular value nomenclature, so that means this is actually finite set. This is a finite set. But that's not what we want to say. We simply say, look, notice that if this is the set, which is here k0 and composed of the regular points, so you know that you can find. So let me say like this. So 10. There exists a epsilon neighborhood of this. No, maybe not epsilon. There exists eta larger than 0, such that the eta neighborhood of k0, k1 has this property that this f will be actually a diffeomorphism, local diffeomorphism around those points, local diffeomorphism from this neighborhood to V, local diffeomorphism. So then there exists an eta such that f, maybe like put it like this, put it like this, bullet, f is a local diffeomorphism from the neighborhood of, so from k0 plus, and this is B, open ball of radius eta, that means the local neighborhood of k0, to a neighborhood, onto an open neighbor, so into, maybe like this, into V, so into V, and the same, G is a local diffeomorphism from k1 plus B eta of 0 into V. So we have it. So this is local diffeomorphism. So that means F, that means in particular, maybe put it here, that for every x prime, maybe for every x prime in here, will have that this df, that x prime, which goes from V to V, is an isomorphism. The same here. dg of x prime from V to V will be an isomorphism. This is x prime. Here. So that's one of the things that you are going to use. That's why. So maybe since we are using these neighborhoods here, maybe let me denote that. So call this one U0, call this one U1. By the definitions, I put here 2 dots. Definition. And now we know exactly that zeros in omegas are exactly k. For f is k0, for g it's k1. So that number 10, we have that I can take the number, call this number 0, and I said this is epsilon, and have epsilon larger than 0, such that I can take this epsilon to be smaller than minimum, and this will be of two values, so infimum, This is x belongs to omega minus u0, and this will be f of x. And then you have infimum x belongs to omega minus u1 for g of x. And I take such a value epsilon which is in between, and that's our requirement for this particular value of epsilon. So now we claim that for every t, and I put here x prime just not to mix up it too much, so belonging to the h minus 1 of 0 intersection 0, 1 times omega, so we have here zeros in omega. It is a regular value, so that means derivative, the dh at that point, which will be mapping r times v to v, is surjective. That means, in particular, which means 0 is a regular value of h restriction 0, 1 times omega. Indeed, if, so we have three cases. If, start with the case number 1, if 0 smaller t smaller than delta, and put here tilde, then we have that x prime must belong to the exactly u0. Why? Because if x prime belongs to omega minus u0, then what do I have? I have here that h t x prime in such a case is equal to f of x prime, and this will be minus psi of t y, and that one is larger equal than f of x prime minus epsilon. And look, this one is definitely positive by the assumption how the epsilon was chosen, so by this assumption. So it will be positive. So if this is positive, cannot be 0, so contradiction. So we get contradiction. Yeah, so it cannot be. So it cannot be. Or we can write it down, maybe like this. Larger than 0, so 4. Maybe like this. 4x we have. So similarly, if you have other one, 0 smaller equal 1 minus t smaller, then we have here that x prime must belong to u1 by the same argument. So what do we have here? So in such a case, we have here that, write it down. So in this case, maybe put it like this. In these two cases, we have that the derivative, put it like this, with respect to x of h t x prime, so I just take one derivative with respect, partial derivative with respect to x, and look, the definition of the function is here. So you see, there are no x in this part, so the partial derivative with respect to x is 0. So in this case, this will be the derivative of h tilde x, but h tilde x in this particular interval is exactly f of x. So that implies that this one is equal to d, and this is no need for x, so this will be just simply f at the point x prime. And as we'll explain it before, we chose this particular set u in such a way, u0 in such a way that, so this is for 1, that this is an isomorphism, and for 2, dx h t x prime will be dg x prime, and this will be from v to v. Again, it's an isomorphism, and if it's isomorphism, that means the derivative of h is actually surjective, because partial derivative is already isomorphism. So this implies clearly that in this case we have here the property that this is every point from this set for this particular two cases is a regular point of h. So now in the case, there is one more case. On the other hand, if we have here like this, the t x prime again belongs to the h minus of 0 intersection 0, 1 times omega is, and t is larger than delta, so maybe like write it down like this, t is smaller than 1 minus that one and is larger than that one, then according to our formulation, then according to our definition of the function, then by definition of psi, let's look at the definition of psi. Where is my psi? Oh, here. So we are here. So this is 1. So we are having here that, let's write it down. So we have that, and here we have here h t x prime is equal to h tilde t of x prime, and that one is equal to minus y, and that one is equal 0, so which is equivalent to say that h tilde of t x prime must be equal to y, and y is a regular value of h tilde restricted to 0 times omega. So that means, so t x prime is a regular point of h tilde. But this regular point means also that shifted by y, that the derivative, but since, put it like this, but since the derivative of h at tx prime is exactly the same as the derivative of tilde tx prime, in this case, we are getting immediately that so tx prime is a regular point of h. That's it. That's it. So that means we proved that indeed all the requirements specified, all the requirements on this homotopy specified in lemma 2 are satisfied. So we have the lemma 2. And now we can move and prove the next lemma, that is basically the last one that will be needed for the existence and uniqueness of the degree, is the lemma number 3. Lemma number 3, and let me specify it. Let f omega and g omega be two admissible pairs such that zero is a regular value of f restricted to omega and g restricted to omega. So what it does in this case, it means that f must be such that f g are c infinity and 0 is a regular value. It's a regular value of both of them. It's both of them. If f and g are homotopic by an omega admissible homotopy, then we have that, I put here like this, sigma, and this the x belongs to the set f minus 1 of 0, maybe I should be more clear, f minus 1 of 0, still not clear, f minus 1 of 0 intersection omega, and that one will be written signum determinant of the derivative of f at the point x is the same as the another sum. This times x belongs to the g minus 1 of 0 omega, and the same signum determinant dg of x. So that means, if you remember, by the analytic formula for the degree that we derived from the axioms, we got that that is actually corresponding to the degree of f, and that would be like a corresponding to the degree of f, and this will be corresponding to the degree of g. So we're just showing that this particular expressions must be equal, and that of course will be used in order to show this among the other things, the uniqueness of this degree is the uniqueness of the degree. So let me do it. Let me do the proof. So proof. So first of all, notice that by lemma 2, there exists a smooth, a C infinity differentiable homotopy H, and this will be like 0, 1 times V to V, which is omega admissible admissible. So this is omega admissible. And we have these two conditions. And for delta, some delta smaller than 1/2, larger than 0, we have two conditions. So this means ht x is equal f of x. This when 0 smaller equal t smaller than delta. And the second bullet is ht of x is equal g of x, and that one is equal to 0 smaller equal 1 minus t smaller. That's what we have. And the bullet number 3, 0 is a regular value of h restricted to 0, 1 times omega. So if this is a series regular value, okay, so that means in particular, therefore, this set M, and I put it like this, h minus 1 of 0 intersection, and this will be 0, 1 times omega, is a compact manifold oriented manifold. Of course, it's boundary. It's boundary of dimension 1. So if this is dimension 1, so we can make this picture. So let me do this picture, so we can imagine exactly what's happening here. So the picture, of course, requires some skills. So let me start right. So this is my space V. This is my space V, and that corresponds to T. T is equal to 0. This corresponds to T is equal to 1. And now, our omega, for example, suppose that's my omega here. So now we are having here the curves. So if you look at the points of the F0, F minus 1 of 0, I put it here, I put it down. Let me move it a little up, and so this will be, I need to be careful. F minus 1 of 0 times omega. So you have here points, several points. So we remember that there are two possibilities. The determinant of f, so determinant of f at the point xk, can have a signum of this determinant, so put it like this, signum of determinant of df at xk. So this is xk, so in this case we have here f minus 1 of 0 into omega, so this will be like a set x1, xm, so this is like x1, x2, xm, so that is equal plus minus 1. If this is a plus, if this determinant is plus, then you have here that your curve, which here is constant, so it means it will be like a parallel, let's say like a constant map, constant curve, is going out. If this determinant is minus, so this is plus, if this determinant is minus, the curve will be going other direction. So the t in this case, the natural orientation of this curve is indicating the increasing direction of t. If it's negative determinant, then this must increase the decreasing direction of t. And in such a case, of course, you have many such such places. And here, of course, you can also assume there is also g minus 1. So put it like this: g minus 1 of 0 will be equal, intersection, let's say, intersection omega will be equal, so this will be like x1 prime up to the xk prime. So all these points are here, so we have here this inverse image here. So this is your x1 prime, x2 prime, and of course there is a similar situation. You have here these curves, and after that they can behave like we don't know. But what we can do, we can just follow such a curve and see what happens. So it is possible that such a curve just turns back and returns, for example, to another point from this plane t is equal 0. Or it can just continue, and if it's not returning, so eventually, because it is admissible map, it has to go and reach the other endpoint. So that's a possibility. This will reach another endpoint. And notice here, when this is reaching, so if this was plus, here it's also plus, because this curve actually shows again the direction of the increasing parameter, sorry, the value of t. So that's the direction how it is oriented. Or it is possible also that there are also some points here belonging to the closed curves in between somewhere. So now, if you look here, so let's say like this, suppose we have here, that one goes here, that one goes here, so this is increasing, and here maybe that one is again, so this is minus, and this will be again plus. And you can see that, okay, possible that this is also returning to the same hyperplane. So we have here this following situation. So it is immediately possible to recognize that there are three, so that the manifolds M, so the manifolds M can be represented as the union of the components. Actually, we can write these joint components. So let's start with the M0. So this will be the components that return to t equals 0. Then you can say the components that return to t equals 1 from t equals 1. And the components that go from one hyperplane to another hyperplane. And finally, we have here 3, which means the components which are closed curves. So maybe let's specify it. So M0 is composed of components, of curves that begins and ends at the points 0t, 0x belonging to this one, to 0 times omega, from the points maybe like this, at, and ends at points from, and this will be 0 times omega. And M1 is composed of curves that begins and ends, and this is actually doesn't matter which direction, and ends at points from 1 times omega. So now, what is M2? Is composed of curves that joins that maybe like this, that run, so that connects, maybe curves that connect 0 times omega with 1 times omega. That's not important which direction, that's not important. And finally M2 is composed of curves which are closed. Okay, so in such a case, it is now easy to rewrite what is the degree. So let's say like this. So let's start with the first one. So we have here that the set. So put it like this: the set of all 0x belonging to n. So that means those are the zeros of the homotopy, and m is the zeros of homotopy H. If I put here 0, that means that's actually indicates that x belongs to the f minus 1 of 0 in omega. So that's exactly this, but now it is mainly indicating the location that the x is a starting point of certain curve from m, and we have here that there are, no, this is 3. So sorry, I have put it 3. So there are 4 types of this curve. So now I can write it down. Signum determinant of this df, and I put here x, and now we can rewrite it. So of course there are two possibilities. So first of all, here we have here that 0x belongs to m0, and this will be signum determinant df of x. So that was the first one, plus, or the curve means can go back to the plane 0 omega, or it can go to another one. So that means this will be 0x belonging to m2, and this will be signum determinant df of x. But now we look here clearly. So every curve that returns has only one beginning point and one end point. And in this case, it is clear that the determinants at the end points are different. If it was positive at the beginning, then it must be negative at the end point, and vice versa. So that means you are getting here that the values like a signum determinant cancel each other for each of those curves. So here can be only an even number of the, so we have here even number of such determinants, and they are basically these curves showing that they are connected. That means pair, put in the pairs, beginning point and end point put in the pairs, giving us values +1, -1, and that means this value must be equal to 0. This value must be equal to 0. So actually we are getting here that this is equal to 0x belongs to the m2, and this is signum determinant of df of x. And now we look at the picture again and we see that this will be now m2. So those curves actually transport us and connect to the corresponding points in the plane 1 times omega, and these values here, corresponding values, have the same sign of the determinant. So basically I can rewrite it down by that this connection actually gives us the following. For each of them I can rewrite them like that, and this is signum determinant, this is df of becomes now the determinant of G. Yes, because that's exactly the determinant on the other side. And then, again, by the same argument as we did it in the beginning of this equalities, so we can write it down that the same as M1, those are the returning curves for t equals 1, signum determinant, and that one is dg of x, and this will be plus, and that one is 1x belongs to the M2, signum determinant of dg of x, and of course that exactly leads to the 1x belongs to M signum determinant of dg of x, which is nothing else than the same as x belongs to the g minus 1 of 0 on omega, and the formula follows. We stop here, and in the following segment we will prove, let's say, complete the proof of the theorem of the existence of the degree. We'll derive the form, we'll use the analytic formula as the way of defining the degree, and we will show that the degree is well defined, has all the properties, required properties, and of course by the formula, an analytic formula, it will be unique. So thank you for